that we're going to be looking at is called use substitution. Make sure all these settings are good. Yeah. This is going to be probably one of the most important topics that we learn in this unit. It is going to be like another way that we are going to integrate. I don't really want to call it a rule. It really is more of a method. And after I teach it, you're pretty much going to have to always be aware that problems will use this thing called use up. It is so important that I actually plan on spending 3 days on it. So my notes aren't going to take the whole period. Like I plan on having at least 20 to 15 minutes at the end of the period so you can get started on the homework and like build on it each day. But use substitution. Before we do use substitution, I did want to review some things from first semester, just make sure we're all on the same page. And that is with, that's super small, the chain rule. Because use substitution, not going to show it to you now, because I think it's better to see kind of where it comes from, is directly related to the chain rule that we know from taking the derivative. And what I mean by that, like if I'm taking the derivative of the sine of 3x from the chain rule, I know that's going to be the derivative of sine is cosine. Helps out a marker. Derivative of sine is cosine. We left the inside the same, then multiplied by the derivative of the inside, which is 3. So that's going to be the chain rule that we learned first semester. What use substitution is going to eventually allow us to do is it is a method of undoing the chain rule. So we know that when we take the integral, when we find the antiderivative, we're like undoing the derivative process. So that was like first semester. Second semester, the problem might look like integrate 3 cosine of 3x. And we will know and eventually figure out that the integral of 3 cosine of 3x would just be the sine of 3x plus c. Some things that make it a little bit more complicated, like in general in math, it's definitely a lot easier to like move in one direction than to like undo it. Like it's often easier to simplify than to unsimplify. So we are going to have to be kind of careful and think about like, normally when we take the integral, like this 3 would be a leading coefficient and just carry straight across. But now when we're undoing the chain rule, it goes away because it really came from the derivative of the inside. So we're going to kind of think of how we undo the chain rule. Looking at some other examples, and then we'll kind of slowly build to kind of taking the integral. First semester, you'll learn how to take the derivative. So if I said take the derivative of 2 plus tangent of x to the 9th, you would know like that 9 comes down in front. The inside stays the same. The new exponent would be 8, and then here's the chain rule. The derivative of the inside, 2 goes to 0. The derivative of tangent is secant squared. There's first semester. This semester, you're going to have some integral, and it probably would be arranged like 9 times the secant squared of x, 2 plus tangent of x to the 8. And we're going to have to figure out how to look at that integral and know that that integral came from the chain rule, which does make it a little bit complicated, but it will allow us to kind of deal with some products that we have with integrals. One mistake I often saw on the quiz is like when people saw 2 things being multiplied together with x, they tried to like find the antiderivative of each part. You can only do that when they're separated by plus or minus signs. So that's going to be one thing we'll look at is like, this is a product, but that secant squared technically came from the chain rule. So we're going to kind of think about like how we would undo that chain rule and works backwards. The process we do that with is going to be called use substitution. How I have my notes kind of laid out today, before I show you use substitution, because I don't want to overcomplicate it, we're going to look at some examples that we can just do without that process. I think many of us can still think through some of the simpler examples just in our head. And then we'll look at the ones like what this thing called use sub is and how that is going to be useful to us. So speaking of use sub, when is it going to be useful to us? Here are 6 questions. All the ones in that first column should be ones that we already know how to do. And then all that ones in that second column will be ones that would require use substitution. You can kind of see the comparisons between them. Like that first one, if I'm integrating 4x to the 5th, really, really easy. That's just the power rule. 4 is a coefficient. Add 1 to the exponent, divide by the new exponent, plus c. We know how to do that one really, really, really easily. In that next column, one that's similar to that, so I still have like a 4, there's still an x, it's raised to the 5th power. This is one where u sub is going to be useful to us because we have something inside of a power. Some students like thinking like, hey, it looks like I would use the chain rule if it was a derivative, then I'll use u sub. That kind of works. That's not always going to be the rule. Like, it's not always going to be obvious at first that it might be u sub. That is kind of like a good generalization for many problems. Like, if you have something inside of something, u substitution is probably going to work. Same thing with trig. So like if I have the integral of sine of x, really easy. We know the derivative of negative cosine would give us positive sine. The one next to that is one that we would definitely have to have u sub. So like there's not really going to be a trig identity I can use to rewrite this one. The issues with this integral right now is we do have like sine is raised to the 3rd power. That's one issue. The other issue is we have a product, and there's no way to kind of rewrite that product. We don't have an integral rule for when sine is multiplied by cosine. That would be one that uses u sub. I put this last one on here because just because you see exponents doesn't always mean it's going to be u sub. Often we have like secant or cosecant because we already have a rule for that. I know the integral of secant squared. The integral of secant squared is tangent of x plus c because the derivative of tangent of x is secant squared. Where I would use u sub if maybe I had a problem that was like the secant squared of 3x because we have kind of like this thing inside of the trig where we need to worry about this thing called u sub. So when we're looking at u sub, we're going to look at some problems where we can kind of do like a shortcut and figure out how to do them without this process, and then I'm going to go back and show you the process. Because again, often we're doing the integrals as like the first step to a much more complicated problem. So like the ones where we can avoid u sub, I'm going to kind of recommend that you avoid it. So we'll just kind of waste time in solving the problem. So like the analogy, like how are we thinking out this? I kind of been saying it all along, but all first semester you did differentiation. The chain rule is to differentiation as the u substitution is to integration. So basically they are one and the same. U substitution is how we undo the chain rule. Do want to be clear though, like we call it the chain rule because it is a rule. It will always follow the same process, like it is reliable and it works. U substitution is not a rule. It's more of a method that helps us solve the problem. So they're not all going to be done the same way. I do think U substitution is probably a little bit more challenging than the chain rule because again, in math, it's often harder to work backwards than it is to work forwards. So let's look at some examples that I think many of us will be able to figure out before we even learn this u sub process. So I have 3 questions. You're looking at 2 of them right now on the screen. But these are integrals. And again, the way that you want to think about integrals is, so if I'm looking at this example, this is the integral of x squared plus 5 to the 7th times 2x with respect to dx. We know that when we find an integral, we're looking for an antiderivative. So an easy way to think about it is like what I have typed in blue, is just kind of think about it in reverse. The derivative of something is equal to x squared plus 5 to the 7th times 2x. That something would be your antiderivative and your answer to the integral. So if I'm looking at this one, normally when we do integrals, like we cannot just integrate each part. So like that is a multiplication sign. You can't just integrate this factor and then integrate the second one. Doesn't work when you're multiplying things or dividing things. Big clue that this is going to be u sub is like, where did this 2x come from? This 2x is the derivative of something on the inside. So we can kind of see that 2x is in the problem because it came from the chain rule. So we want to kind of think backwards. Power rule and all that can kind of still apply. So if I'm thinking backwards, well, I'm going to do the blue part first. The derivative of something was something to the 7th power. What was the power for the original thing you were taking the derivative of? 8. I'm going to go ahead and bring that inside across. Similar to the power rule, we know we want to divide by like that new exponent. So I'm going to go ahead and put like a 1/8 there. We can check our answer. The derivative of this, the 8's going to come down in front. 8 times 1/8 cancels, which is what we wanted. The derivative of the inside is 2x. That does work. So we now know that this integral is equal to 1/8 x squared plus 5 to the 8th, and then don't forget your plus c. You might be asking yourself, like, well, where did that 2x go? That 2x went away when you undid the chain rule. Like, it would have shown up when you took the derivative. So when you undo a derivative, it just kind of goes away. So that's kind of the thinking that we're doing with those problems. Let's look at the second one, and then I have a third one, just kind of make sure all this is making sense. Looking at the second one, I have the integral of the square root of tangent of x times secant squared of x, which is equal to dx. Not going to be a trig identity we can use for that one, like that square root tangent is kind of messy. Big idea again that I'm using u substitution. Where would that secant squared have come from? It would have come from the chain rule, because the derivative of tangent is secant squared. So I know that if I'm undoing the chain rule, then that secant squared pretty much just going to go away, and I just need to figure out the integral of what is in front of it. Well, I know that the square root of tangent is the same thing as tangent to the 1/2. So thinking about this one backwards, adding 1 to the exponent, 1 plus 1/2 plus 1 is 3/2. Divide by the new exponent, 1 over 3/2 is 2/3. Don't forget your plus c. Again, easy way to check your answer is to take the derivative of that antiderivative. So let's check this one. What's the derivative of 2/3 of tangent of x to the 3/2? I know that 3/2 is going to come down in front. That's going to cancel out with the 2/3. 3/2 minus 1 is 1/2. Square root shows up. Times the derivative of the inside. The derivative of tangent is secant squared, so that one works out correctly. So you might be looking at this and you're like, Mr. Brown, like, I just don't think I'm going to be able to figure this out in my head. Like, I just can't visualize undoing the chain rule, which is fine. Like, that's why we have this process called u substitution. But I do think it's very useful for you to kind of see where this is kind of coming from and thinking about how we're undoing the chain rule when we are doing the antiderivative. So I do want to kind of show you like where this thing called u substitution comes from. I know there's a third problem there, but I'm going to skip it for now. I'm going to talk about the big idea kind of right now, and then we'll look at some new examples. So I'm going to show you where it comes from. Again, you won't ever have to like show where it comes from, but I think it's useful to see where it comes from to understand why it works. So here's that same problem we just did. That was the first one, and we saw that that was the answer. We know that's the answer because we talked about it. The big idea behind u sub is where it comes from. Is there's two ways that we can write the derivative of this thing called u. So it's called u substitution because traditionally we just use this variable u. So if I say u prime, that means the derivative of u. What's another notation I could have used that would mean the same thing as the derivative of u? U over dx. Du over dx. So u prime is du over dx. So we have like the Leibniz notation and the Newtonian notation. Those mean the same exact thing. U prime is the same thing as du over dx. Normally we won't split this up like a fraction, like du over dx means the derivative of u with respect to x. But for the sake of u sub, we're going to treat du over dx like a fraction. So let's just do some simple algebra. Multiply by dx on both sides. When you multiply by dx on both sides, you're going to end up with u prime times dx is equal to du. And so it looks weird that we split up the derivative notation, but that is what allows us to do this thing called u substitution. To see why it works, I'm going to kind of show you the u sub with this problem so you can see why it works, and we're going to do a few new ones. U is often going to be like the inside function. So like if I want to take this problem and do it the u substitution way, I would think of this more instead of the integral of x squared plus 5 to the 7th. I'm going to make it easier and just think of it as u to the 7th. We see that u prime times dx is equal to du. Why is that important? Well, u is this x squared plus 5. What would be the derivative of that inside? 2x. So that's the derivative of the inside. And that is with respect to dx. And you're like, why is all this important? That is u prime times dx, what is u prime times dx but du? And what we're getting at is we're going to take a problem that is in terms of x and put it in terms of u. By putting it in terms of u, we're going to have a much easier integral to do. I think all of us can kind of look at this. The original question right here, complicated. The integral of u to the 7th, easy. And then it would be a very easy integral to find. What's the integral of u to the 7th? Well, 1/8 u to the 8th plus c. What do we say u was? The x squared plus 5. So it allows us to kind of take something that's complicated, make it simple, and then allow us to find the antiderivative a little bit better. I do think the theory of why it works can be a little bit confusing, so I'm going to show you one more thing, and if you don't memorize anything today, this is definitely what you want to memorize. So u prime is equal to du over dx. Multiply both sides by dx, and that will give you u prime times dx is equal to du. Doing one more basic algebra, dividing both sides by u prime, you're going to end up with dx is equal to du over u prime. If you don't memorize anything, I would memorize that statement. Again, this is where it comes from, but if you just memorize that, then you're good to go when it comes to u substitution. To show you why I think this is the best way to memorize it, I'm going to look at that second example we did and kind of show you how it actually makes the problem simpler pretty quickly. So here is that second one we did. Again, I didn't do that third one because it just kind of gets repetitive. Here's the statement we're saying. Dx is equal to the same thing as du over u prime. We did this one kind of in our heads before, but I want to do it with u sub. We're first going to have to identify u. I'm going to, in this case, let u be that tangent of x. I'm going to identify u prime. U prime is just the derivative of u. What's the derivative of tangent? Secant squared. And this kind of method gets its name because you're literally just doing some substitution. So let's go to have the integral. It was the square root of tangent. I'm now going to call this the square root of u. What is dx equal to? Dx is the same thing as du over u prime. So I have the secant squared. It hasn't gone away yet. So I have the square root of tangent times secant squared. Dx is du over u prime. So there's my u substitution. And then you'll notice that certain things will happen. What do you notice about those secant squareds now? They cancel. That's the goal. Now all the x's are gone, and we have a nice integral, the square root of u. Now we're in terms of u. There's the du, and that becomes a pretty easy integral to find. That's u to the 1/2. 1/2 plus 1 is 3/2. 1 divided by 3/2 is 2/3 plus c. But what do we say u was? U was the tangent of x, and that's where that answer would come from. So there is like a process. There are certain things you have to find. There are going to be some problems that many of you will eventually be able to just do in your head, which is what I would expect. But there's going to be plenty of examples where you're going to want to kind of follow this process in order to find the antiderivative of it. So the first thing that I had to do when I did these problems is I had to choose a u so that things worked out nicely. And that sometimes is the hardest part with u substitution, is choosing a u that works. So how do we choose u? These are not going to be steps. These are more going to be guidelines. I don't even want to call them rules. They're just kind of like, hey, if I'm trying to choose u, these are some things that I just like think about and consider. The first thing I consider is I'm going to choose u that is inside another function. Kind of like when we talked about chain rule and stuff. Those of you coming from Ms. Kennedy, I think she uses the term like donut and donut hole. So like you're looking for like a donut hole. I don't teach it that way, so I don't really know what that means, but we're looking for the inside of a function. Other things you're looking for, u prime should be fairly easy to find. Again, the whole idea with this is it should be simplifying your problem. So u prime is a derivative. So like if you're taking the derivative and it's like some weird complicated like product rule with the chain rule, then you probably chose the wrong u because you're making the problem more complicated instead of simpler. And then the most important thing you're looking for is u prime should be elsewhere in the problem. Or a constant multiple of u prime. The reason why we want to have a constant multiple or for u prime to be exact in the problem is, again, this whole idea is we want things to start canceling out, so it is a simpler problem. So like if you don't have a constant multiple of u prime, not all your x's will cancel, and you're going to be left with a harder problem to do. And then fourth thing, very teacher of me, is just going to be like practice. And I don't take that lightly. Like there's going to be many of these problems where you can like look at it and you're like, I know what u is. There's going to be some where you really want to kind of debate with yourself of like, what is the u so the problem works out nicely. And that's just kind of being exposed to a bunch of types of problems. Because there can be some weird ones, especially like when you have trigs. Sometimes it can be hard to determine like which trig should be the u and which one is not the u. And then also as we all add all the other rules that we want. So I'm going to look at one example for now and then have you try two of them on your own. And that's actually where I'm going to stop today's notes at. I'm going to start with just an indefinite integral. So we know the indefinite integral is you're just finding the antiderivative plus c. U substitution does show up with a definite integral, but there's like a lot of special notation things you have to be careful with. So I'm going to spend just tomorrow on the definite integral. So I want us to integrate cosecant squared of x over cotangent cubed of x with respect to dx. Here's the reminder. Big thing if you need to just memorize something, just know that dx is the same thing as du over u prime. Say you're taking your test and you can't remember that, or you just want to be sure that it is dx is equal to du over u prime, you can derive it again pretty easily. Just remember that u prime is the same thing as du over dx. Cross multiply, and then solve for dx. So you can like derive it pretty easily, or just memorize that dx is equal to du over u prime. And so to start off these problems, the first thing you want to do is to always choose your u. Again, you want to choose a u that has a fairly easy derivative to find because you want u prime to simplify the problem. You also want u prime or a constant multiple of u prime to be elsewhere in that problem. I'm going to go off to the side and show you some bad u's to choose. Only because I think it's helpful to kind of see when you're doing these problems, like maybe you choose a u to know when you're going down the wrong path. One example would be a bad u, so we know that sometimes u will be what's inside of the function. So I think it's pretty logical to look at this and be like, hey, this is cosecant squared. Let me let u be just the cosecant of x. I would argue that that would be a bad choice for your u. What's the derivative of cosecant? It's negative cosecant of x times cotangent of x, which is not going to be very useful to you for simplifying the problem. So like u is cosecant of x, but you have a cotangent cube left over. Its derivative only gave you one cotangent and an extra cosecant. So like that would not be useful. Not everything will cancel. You're kind of going down a wrong path. Another bad u to choose. And again, it's a very logical one to choose. Like we'll see a lot of examples where the denominator will be your u. You might just let u be this cotangent cubed of x. Like you're like, I don't like cotangent cubed. I want to go away. So I'm going to let u be the cotangent cubed of x. That would also be a bad example, mainly because it has an overly complicated u prime. So still have to do all your derivative rules. Those aren't going away. The derivative of cotangent cubed would be 3. That would become cotangent squared of x times the derivative of cotangent, which is negative cosecant squared of x. Looks like it might be somewhat useful, like it had a cosecant squared, the problem had a cosecant squared, but you kind of have all this extra stuff that's going to make it more complicated. What's going to be the best u for this problem? The best u is going to be what's inside of the cotangent cubed of just choosing the cotangent. How do I know this is going to be the best choice to use? Well, what's the derivative of cotangent? Negative cosecant squared. And we do see that there is a constant multiple of u prime in the problem. Like there is already a cosecant squared. There's a negative there, but that's just a constant multiple. It's just a number, not a variable. So once you determine that, then you can go ahead and rewrite it. So I have the integral cosecant squared of x. Here's where it gets its name. We let u be cotangent, so this denominator is going to turn into u cubed. And then what is dx equal to? Dx is equal to du over u prime. So instead of writing dx in the problem, I'm going to write du over u prime. If you do it correctly, you should end up with a simplified integral. This one does look like it's going to work out pretty nicely. Cosecant squareds cancel out. And then you just want to clean it up a bit before you find an antiderivative. I like moving constants onto the outside of my integral just to kind of like get them out of the way. So you can never move variables outside the integral sign, but if it's a number or a negative, then you can move it on the outside. So I'm just going to stick that negative on the outside, again, just kind of getting it out of the way. Cosecant squares cancel, so I have 1 over u cubed, and then we had a du. And that du is important because now it says we're doing this integral with respect to u instead of what it was originally with respect to x. That should be an easier integral to find. Can't technically integrate it quite yet. What would you need to do to that integral before you found the antiderivative?
Put u on top.
Put the u on top. So we can't integrate it with that u in the denominator. So I can bring it up top with a negative exponent. And now we're happy because that's just an easy, simple power rule. So when I go to find that antiderivative, coefficients carry across. You add 1 to the exponent, -2, divide by that new exponent. So I'm going to divide by that -2, plus c. Careful and don't leave your answer like that. This was a problem in terms of x, not in terms of u. I'm going to cancel out both those negatives, so you have 1/2 u to the -2 plus c. What was u? Cotangent of x. Some of you might rewrite this as well by sending it back to the denominator with a positive exponent and have that as your answer. But both those answers will be fine and correct. Questions on that problem or that process? I will say, so that's like the most work you would probably show. We'll be doing u sub enough, and many of you are smart enough to like skip steps. So like first off, please don't skip steps if you need to show them. Like show them if you need to show them. But honestly, many of you could probably like just show your u and your u prime, and then just jump straight to the rewritten version of it. And then once you have the integral, jump straight to the answer. You don't have to like clearly show the integral with u. Like if you find the antiderivative and plug in u at the same time, perfectly fine with me. Try, I'm going to skip ahead. So we're going to do the definite integral tomorrow. Talk a little bit more about notation tomorrow. If you're following along in OneNote, it's a slide that says try simpler. Go ahead and try those for me before we go over them. Oh wait, I lied to you. Don't do those yet. Just do the try these slide. Those are a little bit easier than those. So I'm on the try these slide. And again, if you don't memorize anything today, at least memorize that dx is equal to du over u prime. But take a moment to try those two. We'll go over it, and this is actually where I'm going to stop today's notes at. If you're checking your answer, there's what I would choose for my U for those two. Clearly I'm not done, but that would be the first step for both of them. U prime is pretty easy to find once you identify your U. I'm gonna give you a few more moments to finish those before I finish them. So this first one, I do want to be clear because I want to make sure we understand why we have to do U sub again. Like we do have a product, we can't just integrate each part of a product. It doesn't work that way. Also, there's no way to like FOIL or distribute to rewrite that one. So it's stuck written the way it is. U sub we can kind of see is going to be a good idea because like the derivative of the inside is kind of on the outside. Letting U be x cubed minus 2. U prime is going to be this 3x squared. So let's go ahead and rewrite it. So I have the integral of x squared times the square root of u, dx is du over u prime. I know I'm on the right track because the constant multiple of u prime is elsewhere in the problem. So the x squareds do cancel. I like moving my coefficient on the outside. Do be careful when you move that coefficient on the outside because that's du over 3. So the coefficient on the outside is going to be a 1/3 the integral. And I'm going to go ahead and rewrite the square root of u as u to the 1/2 du. So now we have a simplified integral. So now I can go ahead and find its antiderivative. 1/3 is the coefficient, so it carries across. U to the 1/2. 1/2 plus 1 is 3/2. 1 over 3/2 is 2/3. I'm going to go ahead and plug in the u now. What do we say u was? U was x cubed minus 2. And of course, don't forget your plus c. You can leave your answer like that, but most of you will probably multiply those coefficients to have a final answer of 2/9 x cubed minus 2 to the 3/2 plus c. Again, easy way to check your answer, take the derivative of that, simplify it, and you will end up with what you started with. Questions on that one? All right, second one, kind of same. We have a fraction, we just can't integrate each part. I'm going to let u be the 1 minus 2x squared, so u prime is going to be negative 4x. Rewriting this, I have the integral of x over u squared, dx is du over u prime. Looks good because the x's cancel out. Negative 4 is in the denominator, so I have negative 1/4 on the outside. This is u squared in the denominator. I'm going to go ahead and bring it up with a negative exponent with respect to du. And then this becomes a pretty easy power rule problem to do. Negative 1/4 is the coefficient. I have u add 1 to the exponent, divide by the new exponent. Don't forget your plus c. What was u? U was 1 minus 2x squared. That answer's fine, kind of ugly. That's really going to be a positive 1/4, 1 minus 2x squared to the negative 1 plus c, or 1/4, sending that to the denominator. Try that again. And having 1 over 4, 1 minus 2x squared to the first power plus c. Again, all those answers are the same, but those are just kind of 3 different ways to write it. Questions on that problem? All right, so that's where I'm going to stop at again for today. Like, these problems definitely can get more complicated. Tomorrow, what we're going to look at, and again, you can kind of see if you're looking in OneNote, we're going to talk about the definite integral. Because again, there are some things we have to be very particular with when we do the definite integral and use substitution. We'll talk a little bit about notation that's important to show. And then I will talk about a special case where not all of your X's will cancel, and kind of how you remedy that situation with U sub. The homework I want you working on, I did want to kind of explain it a little bit, because it looks like it's two different assignments. That's just because I forgot to update what's on the calendar before I shared it. So on the calendar, if you're looking, it tells you to do like 8 through 60 evens and skip 32. I changed it in OneNote when I shared it with you, but I forgot to change the assignment. On OneNote, if you look at it, it does tell you to do just multiples of 4. And that's all that I'm going to require you to do from that page is multiples of 4. If you want more practice, then go back and do the evens. I'm like only going to count the multiples of 4. Do skip number 32 no matter what. You don't have to know how to do number 32. I might recommend, so again, like this is all we're doing this week. I might recommend going and doing all the evens first. Check your answers. If you got all the evens correct, then you probably had enough practice. If you had to look at the answer key a lot while working on it, or you got a lot of your answers wrong, then I'd probably go back and do all the evens instead of just the multiples of 4. Again, you can't do all those right now. We still have to do a few more things, but that will at least let you get started. The first few problems on that homework are going to be the pretty like simple U sub ones that you can do pretty quickly. Do want you to at least start that, so like when we do the definite integral, it goes fairly smoothly. If at any time this week you're just feeling like super eager, there's nothing really else big topic-wise for us to learn. So you do actually have enough knowledge to do homework 5 as well. So like if you finish homework 4, you're more than welcome to start homework 5 before Friday. Next week we'll just be reviewing, so finishing up the briefcase finder and quiz corrections, and then your test is going to be on Wednesday. That concludes like the notes portion. So if you're at home, you're welcome to leave, I guess. If you want to hang back and ask any questions, and you can do that